This is a long lecture, the longest in the entire course and one of the most mathematical. But finally, we have arrived at the point of introducing neighborhood method. Up to this point, everything we talk about is about individual row or individual column in the movie user rating table or matrix. But now we are ready to go into the global structures. And the way we go into the global structure is by defining a neighborhood Li for each, say, movie I. We can also look at this from a user point of view. We'll instead just focus on the movie-movie correlation. So you can think of two columns representing the two movies. And we want to look at how different they are. In other words, define a pairwise statistical correlation between the two movies. And then we look at another pair of movie, still movie I, but instead of comparing with movie J, we compare with movie K. And look at the ratings from between this and this two columns. And then we're going to pick up all those movies that are somehow very similar or very dissimilar compared to movie I. Both kinds of movies would be very useful. So this is what we're going to do. We first define a similarity metric between two movies, and then we will search through all the movies out there and then pick up a subset of those that are either very similar or very dissimilar compared to movie I and call that the neighborhood Li. And we leverage that global information in making predictions about users liking or disliking this movie I. So this idea can be illustrated quite nicely through a simple picture. Suppose we've got just two movies and two users. So we can easily compare 2 points on 2D grid. The 2 points are the movies A and B, and we've got two users, 1 and 2. The points are the movies, and the axis are the users. So movie A is getting a rating of 5 from user 1 and 1 from user 2. So movie A is getting a 5-star and then a 1-star from these two users, whereas movie B is getting a 2-star and a 5-star from these two users respectively. As you can tell, that these two movies are kind of very different. Okay, they are basically liked or disliked in an opposite polarity by these two users. And indeed, this means that this angle theta is kind of big. What is this angle? This is the angle between two straight lines. One is the line from the origin to this movie's coordinate, and the other is from the origin to this movie's coordinate. And if these two coordinates are far apart, one quantification of that is the angle theta here. If we measure the cosine of that angle, that is a particular number, and we use that number to describe how similar or dissimilar A-B movies are. This is called cosine coefficient. It is a particular instance of similarity metric that we'll be using here. So how do we write down the cosine coefficient here? I'm going to say the cosine coefficient between two movies ij is called dij, and if you remember from basic geometry, analytic geometry, it's really this point viewed as a vector from origin to that point. Okay, call that a vector Ri. It's a vector. Transpose Rj, that is this point viewed as a vector from the origin to that point, divided by the normalizations, that is the size of I, L2 norm, and the size of J, also L2 norm. So we can view these two ratings for two different movies as two vectors, Ri and Rj, and the cosine of the angle is the standard formula, which is just their inner product normalized by the sizes. And this in the longer form just means Rui and Ruj summing over all the U's who have rated both movies I and J, that is. That is the inner product of these two vectors, divided by the square root of, just by the definition of L2 norm of the two vectors, Rui squared summing over all the u's, the same set of u as here in the numerator, and summing over the same set of u are uj squared. That's just the L2 norm of these two vectors. So this dij is the cosine coefficient defined as such geometrically as the cosine of the angle theta and algebraically defined as such. Now, because we have already shifted the R data from R to R minus the baseline predictor R for each UI pair, we call this R tilde UI at the end of the last segment of the video. So strictly speaking, we should put tilde here. So all looking at the R tilde value that has already subtracted the influence of the baseline predictor. So now what we need to do is to look at all the pairs of movies ij except movie ii back to itself, and then compute this relationship. So at this point, we have for each movie I computed the dij for all the j's out there. I've got a list of numbers. Let's arrange these in descending orders. Okay, these are the dij values, and maybe movies 5, 8, 10, 2, and so on, with respect to movies say I equal 1, the first movie. Okay. All right, very good. If you look at this and say some of these are real big numbers, some of these are real small numbers, real negative numbers. Again, remember, this actually can be either a positive or a negative value. So we will say those that are very positive and those that are very negative are both useful because they are very similar or very dissimilar movies. So let's just look at the absolute value of dij's. And we want those that are big to be included. Okay, so we'll pick the top, say, 5 movies. Top either meaning they are really big here or really big here. Okay, and that will define what we call the neighborhood, a list of other movies with respect to this given movie I. So for example, L1 could be movies 5 and 8. Let's say there's a movie 21 down here, 21. Okay, now I say who determines how big the set is? How long is the list? Who determines basically the cutoff threshold of the dij value? Well, the one that would be determining this is you, okay, the recommender. So there are quite a few rules and guidelines in determining how big is this list. If you make it too big, then you are indeed incorporating the comparative information with respect to many other movies, but some of them are so weakly coupled with this movie that it doesn't quite matter. So just adding too much noise. On the other hand, if you include too few neighborhood movies, then you're not fully leveraging all the information, and then you are losing precious information about other movies. So that's not good either. We won't have time to go into the exact art of picking the right size, and that's indeed part of the reasons why it took many computation for these teams to compete in the Netflix prize. But roughly speaking, the idea is that if you like movies, say Schindler's List, and say Life is Beautiful Life, then maybe you like Dr. Zhivago. If you dislike E.T. or dislike Lion King, then maybe you also dislike, say, Toy Story. Okay. So that's the idea. The idea is that we're going to look at all these movies as points in the space. Those that are very close by this cosine theta metric, we'll call them neighbors. And therefore, for each movie I, we will define a neighborhood by the absolute value of these cosine coefficient values. So now that we have defined what is the metric cosine similarity, and from there we have defined what is a neighborhood for each movie, we can finally define the predictor based on that information, called the neighborhood predictor. So the neighborhood predictor would be denoted as r hat ui, but we have already used that symbol to represent the baseline predictor. Let's add sup n. This n does not mean the number of users of movies, is a shorthand for neighborhood. Okay, so we want to find out what is r hat sub ui sup n. This is basically the original baseline predictor, now plus what we learned from these neighbors. We learned from these neighbors that if a neighbor movie J in the shifted rating R2D, okay, again R2D is just R minus R hat, in this shifted space, depending on whether J is positively correlated with movie I or negative correlated with movie I, it's going to give us some information. So we want to add up those information, summing across all the movies J indexed by J in the set L sub I. So we have to weight each such rating by a neighbor movie J in some way. What should the weight be? One choice is just let weight be the cosine coefficient itself, Dij. Now this may not be the best choice. We just don't have time to go into optimizing this particular choice of the weights. So let's say it's just Dij. So if Dij is positive, we're adding to the prediction. If it's negative, we're subtracting from that. And then we have to normalize somehow, right? Because we might be adding a lot of these movies in the neighborhood. So we have to divide that by the magnitude of the weights. The weights can be, it's just Dij absolute, summing over J in the neighborhood for movie I, Li. Now, why do we put absolute sign here but not here? Well, because in normalization, if you don't put absolute value, the positive and negative Dij's will cancel each other. So that's not the intention, to count their size. But in the numerator, if we add the absolute value, then we get confused whether J is very similar to I or very dissimilar to I. That's why when we calculate the influence by neighborhood movies J, we use the actual Dij, which could be positive or negative. But when we normalize by their size, we have to use the absolute value of Dij's. Now you can make it even simpler by just making the weights 1. You simply just count, add up the R2Ds and divide it by the size of the neighborhood. That's it. That turns out not to be performing very well. So we use a slightly more involved weights here. All right, so this is what we have been looking for in the last 80 minutes. This is the neighborhood predictor that will enable you to get quite far ahead in the Netflix prize competition. It composes of 2 parts. One part is the baseline predictor. Again, how do we get to the baseline predictor? Very simple, by solving the least square problems involving these BUs and BIs. Because the baseline predictor, R hat, is just the lazy average predictor plus BU plus BI for each UI pair. Okay, so solve least square based on the ground truth, train your parameters, U BI star BU star, stick it into the predictor, you get R hat. The second term in the neighborhood predictor is the actual neighborhood information. Again, we use the cosine coefficient as the metric. And then for each movie I, we define a neighborhood of a certain size. And then, based on that, we say all those movies J in that neighborhood set will be weighted with a certain weight, for example, the Dij themselves, and then normalized. This is the total influence in the prediction of UI. So now let's summarize what we have at this point. The neighborhood predictor for collaborator filtering in Netflix consists of 5 steps. The first step is train your baseline predictor. R hat equals R bar plus BU plus BI. I don't know what should BU, BI be, so I'm going to look at this prediction with the actual UI, RUI, and then look at the difference squared, solve the least squares problem. That will give me the BU, BI, and therefore the baseline predictor. Okay, once you have the baseline predictor, let's call that R hat, then we can subtract R from R hat and get this shifted R2D, okay, which could be positive or negative depending on what's your R hat. And then from the R2D we can compute a similarity metric. If we collect all these into a matrix big R2D, and from this big R2D we get another matrix D, where each ijth entry of big D is simply the Dij that we computed as a function of these R2Ds. Once we have computed this Dij, we can define a neighborhood Li for each movie I, consisting of a bunch of movies, very similar or very dissimilar from movie I. And once that's done, we can now plug everything into the R hat N UI formula, which we just shown on the previous page, because we have now all the ingredients, including the baseline, the Ds, and the R2Ds. And that will give us the final predictor, which we can collect all the UI entries into a particular table or matrix R hat sub N, M for neighborhood method.